Hello, everybody. I'm Andrew Kennedy, visiting from MSR Cambridge. I'm here, well, for another week. I've been here about a month, working with the product team on the CLR. But today I'm going to talk about a different project. That's a compiler for the functional language StandardML that targets the .NET Common Language Runtime. Before I do that, just a little introduction to the group that I'm from. So we've got this programming languages group in Cambridge called Programming Principles and Tools, headed up by Luca Cardelli. And then there's people who you'll know of if you're familiar with Haskell: Simon Peyton-Jones, Simon Marlowe. And then there's a few of us working on the ML compiler. That's Nick and me and Claudio. And Tony Hoare, who you all know, of course, and Andy Gordon and Cedric Fournet have done a lot of work on security and programming languages. And so there's about perhaps 50% of our time has been spent on .NET-related things, and the remainder on more theoretical stuff. So what I'm going to talk about today is targeting a functional language at the .NET Common Language Runtime. So I'm going to give a brief overview of the language itself for those of you who aren't familiar, and then talk about our compiler, in particular focusing on how we do interop with .NET Framework libraries and the implementation, any challenges we met in trying to target a functional language at what is essentially an object-oriented runtime. And then at the end, I'll do a quick demo of some work in progress that's integrating this into Visual Studio. So, well, this is really a marketing message for the .NET people, but I do believe it. I mean, .NET does provide a big opportunity for people at Microsoft and outside, both to direct language design and to implement existing languages on top of .NET. So there's three things, really. The CLR provides a bunch of services that make it much easier to produce compilers. So you don't have to worry about garbage collection and low-level compilation and debugging and all this stuff because the CLR does it for you. And secondly, once you've got your new language up and running, you don't have to re-implement lots of libraries because they're already there. And thirdly, you maybe have more of a chance of evangelizing your language and getting it used outside of research because it's much easier to write programs that are written in a mixture of languages using the Common Language Runtime. So for those of you who don't know, SML, that's StandardML. So everybody asks what the ML stands for. It's just meta language, which doesn't mean very much now. It was originally used for automated theorem proving, and that's where it was being used as a meta language. But it's now really a general purpose language. It's the only real language with a complete formal semantics, and it's been very influential in programming language research over 2 decades probably now. There's 2 variants of the language. There's the French one, Camel, very popular, and there's StandardML, the one that's being standardized to a formal definition, and that's what we've implemented. And it's been applied to various domains. So I'm going to introduce SML in just 3 slides, and I'm going to focus on 3 features that are very characteristic of all functional programming languages, really. And of course, these turn out to be the challenges for the implementation. Do jump in with questions whenever you want. So the first feature is data types. So you can define new data types very directly. So here we're defining a type of binary trees. So these things are called constructors, and these are the ways that you actually construct elements of this type. So a tree is either a leaf or it's with no data in this case, or it's a branch that's got a key, which in this case is a string, some data, and left and right subtrees. And then given such a type, you can define functions that do case analysis on their arguments. So this is a tree, and it's saying, I'm going to deconstruct that tree by saying, is it a leaf, then do this. Is it a branch? If so, then go down here. And another characteristic feature of functional languages, most of them anyway, is that you don't have to write types. The compiler will infer them. So find here has the inferred type tree paired with string and returning int. So this star means paired with, and arrow is the function. Okay, so the second characteristic feature is first-class functions. So I can now parameterize my find function on the comparison function that's being used rather than fixing it to be string.compare. So now the type of find is it takes a tree, it takes a string, and it takes a function, which gives the ordering. And here it's being used by, I'm passing in an anonymous function in this case that does case-insensitive comparison. The third feature is parametric polymorphism. So I'm going to generalize the data type so that rather than fixing the type of key to be string and the type of data to be int, I parameterize on the key type and the data type. So these things with the sort of tick mark are type parameters. And then the type of the function correspondingly involves this type parameter. So it's taking a key data tree and a key to search for and an ordering function on keys and giving me back some data. So that's SML. So what's SML.NET? It's a compiler for SML that targets IL. That's the Microsoft Intermediate Language, well, CIL, the standardized variant. That's verifiable. So that means that it passes the type checking that the runtime performs for untrusted code. So that's all very well. I mean, we've got lots of SML compilers. Why would you want to target the CLR? Well, the reason being all this infrastructure it gives you. So the research issues are, can we compile something that's rather different from the Microsoft languages, C#, VB, and so on, a polymorphic functional language, down to a runtime that's right now monomorphic and, for the most part, object-oriented? Well, obviously the answer is yes. And we managed to support the whole of standard ML. But is that code fast and compact? Well, only because we play lots of tricks. Because the runtime doesn't directly support a lot of the features that we want. So we have to play tricks to produce fast and compact code. And the third question is, how easy is it to interoperate with .NET Framework libraries, which are object-oriented in style, very different from ML libraries? And so what we've done is we've actually extended standard ML to support all the features of what's called the Common Language Specification. That's the subset of the CLR that people are supposed to use when they write libraries to be used across different languages. And you'll see how slick that is. I hope you'll think it's slick. And then we've got some work on integrating this into Visual Studio, which I'll show you later. So at last, I should say that it is available. So you can find it from that website. It's actually hosted. That'll redirect you to the University of Cambridge Computer Lab, where it's hosted. And it requires, at minimum, the redist of the .NET Framework, which is the bit of the .NET Framework you need to run programs. I'd probably recommend getting either the SDK or Visual Studio.NET if you have it. And the distribution contains the binaries and some documentation and a few demos. And you can optionally download the sources as well, which require Standard ML of New Jersey right now to build. So it's a completely liberal and open license. There's no... yeah.
What's stopping you from self-hosting? What's missing in NeuroML?
We can actually just about bootstrap, but it's not particularly nippy. Pretty slow right now. So in the next section of the talk, I'm going to talk about how we tackle interop with .NET libraries. So before .NET, interop was kind of ugly. There were two ways of doing it. If you've got a high-level language like SML, you either go through some bilateral interface, that's an interface to one other language, typically C, where you have to give directives to explain how to marshal arguments and return values and calling conventions and so on. So examples of this are the Java native interface and the OCaml interface for C. They tend to be tied to one implementation and only used by experts. So typically an expert would wrap up some external library and give it a friendly interface for ML or Java or whatever. But it's only experts who would do that. And the second approach has been having some interface definition language that lets multiple languages communicate and then have particular mappings of that interface definition language down to features of particular languages. And examples of this are COM and CORBA. And particular language mappings, so there's a COM binding for Camel. HDirect is a COM binding for Haskell. MCORBA is a CORBA binding for Mercury. But there's problems with that approach too. Well, you have to write this IDL, which people don't like doing. Memory management is often tricky. You have to do reference counting, and you've got references between different heaps. And it tends to force you down to a lowest common denominator. So in .NET, instead, because all the languages share an infrastructure that provides the heap, garbage collection, and so on, means there's none of this reference counting stuff. Type systems shared, so you don't need to marshal. So strings in ML are strings in C#, say. And even the exceptions are shared, so you can throw an exception in ML and catch it in C#. So all this sounds very good, but SML is not object-oriented. So we're going to have to do some work to make this clean. So given the CLR, we could do a number of things. Instead of extending the language, we could actually just provide lots of wrappers that give a kind of functional feel to a CLS library. And this is the approach that they've been taking with Haskell and Mercury implementations on .NET. But it needs a pretty rich type system to express some of this stuff. So Haskell's got a very rich type system, and through encodings in its type class mechanism, you can actually sort of mimic object-oriented features. But ML's not quite that far. You could redesign the language completely, so essentially make SML object-oriented. But rather than go that far, we've got a sort of middle way, embrace and extend, I like to call it. So we embrace existing features of SML where they're appropriate. So where they match very well what's coming from the CLR, then we just reuse SML features. But when that doesn't quite work, we'll just extend the language. I mean, bearing in mind, this is only going to be used when you want to interoperate. We're not really thinking of making it an object-oriented language where you use it generally. And a third thing is we're living within the CLS, the Common Language Specification. We're not trying to export ML-specific types like data types to other languages. So here's an extract. I don't know how well you can see that. This is some SML.NET code that basically pops up a file dialog box, I think. So here we're opening some what look like SML structures. That's the module of ML. But actually they're CLR namespaces, which are sort of mapped into SML structures. And here's an ML function, but this open file dialog call is actually a constructor coming out from some class in .NET that's mapped into an ordinary ML function with no arguments being represented by the ML unit value. So far we haven't actually extended the language, but if you look down here, we've got a syntax for method invocation, virtual method dispatch, that didn't exist in SML. We're representing null values from .NET by the option type in ML. So you have to be explicit about testing for null. And the type system knows when something can be null and can't be null. But you'll see this is an example of types just mapping straight across. A .NET string is an ML string. So I'll give a quick demo. So those of you who were ICFP a few years ago might remember that they had a programming competition. They have one of these each year where they set a task, and you can choose your language to implement that task, and you have 3 days. And the task, whenever this was, ICFP 2000, was ray tracing. So you were given a specification of a little modeling language, and the task was to read the modeling language in and to render a scene. And they had entries in all kinds of languages, and ML, unfortunately for us, Camel, was in first and second place.
I forget, what's the measure?
The measure was A, correctness, so a lot of programs just fell over, and B, performance, I think. So, fortunately for us, someone else actually translated the Camel code into SML, John Reppy. What we did was added interop. So the way that the task was set was it would produce just a file, which is fine for a competition, but a bit dull. So we added interop so that we could render this on the screen, and then you can run it on .NET. I think that's going to work. Let's click. Let's see. So yeah, this .gml file is a sort of little modeling language that was devised for the competition. And okay. That was the main example image, I think. But let's try one. Whoops. It's quite a nice fractal. Slightly more challenging image. Okay.
What was the last bullet there?
Performance, right. So on this example, we get very good performance. It's actually twice as good as SML of New Jersey. But on others, we're twice as bad, even worse than twice as bad. So work that's ongoing is, work out why this is. Because we're doing quite a lot of optimization. But
how do you compare to MLton?
I think probably on this example we're on a par. So on sort of floating point intensive stuff, or where there's not much memory allocation essentially, then I think we're not too far off them. But anything involving data types and closures and things seems to be not so good.
And one last comparison. And what about the original Camel implementation?
I don't know, actually. I mean, the point that they did translate into SML in order to do performance comparisons. I think probably roughly the same, because I think SML was, NJ was somewhat slower. Yeah. I mean, this is really just relying on the JIT, because we're compiling down to as much as we can. I don't know how we can do much better. So now I'll talk a bit about implementation. So it has to be said that despite being called the common language runtime, it's not what a functional programmer would have designed. So in its favour, I'll say it's got support for tail calls. It is possible to compile ML, and the performance results are pretty good considering. So the challenges are, like I said, those features that are characteristic of functional languages: data types, first-class functions, and parametric polymorphism. Oh, and if you were doing Haskell, you'd also have laziness, which is even more of a challenge, I believe, on the CLR. So I'll start with a very simple feature rather than focusing on those three, just to illustrate. So ML has the notion of tuples, tuple types, and of course these just compile down to classes with fields for the components of the tuple. Now, tuples, I mean, this is standard stuff and independent of the CLR, really. Tuples are allocated on the heap, so we want to try and flatten and avoid that heap allocation where we can. So we do. So functions, in certain situations, are flattened, with arity raised, so that we don't allocate a tuple. And likewise, data types that involve tuples. Now, a particular problem we have, due to the absence of polymorphism, is for every tuple, we generate a new type, a new class. And that could be a problem. So we try to share classes where we can. So, for example, we disregard the names of fields when you've got record types that are isomorphic to tuples. And we even, well, not yet, but we're going to do this, I guess, reorder things so that we share. Yes. Yeah, so as usual, optimizations are in conflict with debugging. Yes.
This is also one reason why you do a global compilation step, because if you had a separate compilation, you would have to match up the names in some way.
Right, yeah. So, yeah, I should emphasize that, yeah, we do take advantage of the fact that we're doing whole program compilation. And if we were trying to support separate compilation from the outset, then a lot of this we wouldn't do. So data types, so map into sort of three varieties. We do special case on enumeration types where all the constructors are nullary, and that just maps down to int in the CLR. Where we can, we make use of the fact that there's always a null value available. So the obvious example is lists. If you've got something that's an int list, which is either empty or it's a cell with a pair, then we use the null value to represent empty. Otherwise, allocating an object with an int field and an int list tail. But otherwise, we have to do something more general. So the obvious thing to do when compiling data types is to sort of use the inheritance idiom. So for a particular data type, you define an abstract class. And this is, I guess, what you would do if you were programming C#. And then for each constructor in that data type, you have a subclass, concrete subclass. But we don't do that. Problem being, there's no efficient way of switching on type in the .NET runtime. You can only do one at a time class tests. And also, this would generate a lot of classes. You have one class for every constructor, and then one class for every data type. So instead, we play this bit of a hack, really. We have a sort of universal data type class that has a tag in it, which represents the actual constructor. And then for every constructor type, we subclass that. So here we've got what the example was now. What have we have string. Oops. So we had a string and then two data types there. But the point being here that you can share these classes across different data types. So the way the case would be implemented is you switch on the tag and then cast down to the known class that you know it is. And switching on a tag is very efficient. Okay, so second feature that's a challenge, of course, is first-class functions. So sometimes the function isn't used in a first-class way. So in that case, we generate a static method, or even just a basic block. But otherwise, we want a closure, that is, a pair that consists of the code pointer and the environment, that is, the three variables of the function. So here's an example. I define a function translate that refers to a variable from an outer scope and then pass it around as a first-class object. So we need to construct a closure for translate that has xinc in its environment. So again, we could use the sort of inheritance idiom. You have one class per function type, and the function, and that's an abstract class with a single method that's just the function application method, in this case taking an int and giving back an int. And then for each function definition, you define another class that implements that method by providing a body, that's the body of the function, and the environment is represented by instance fields of the class. So in order to access xinc, we go through self, through this. So downside, again, is that loads and loads of classes are generated. You end up with one for every function type and one class for every function definition. Now, those of you who are familiar with .NET might say, well, why not use delegates? That's .NET's version of first-class functions. Well, for a start, it would also require one class per function type because they're based on name equivalence. So you'd need to define a delegate for every function type. And you wouldn't be able to share environments either. You'd need classes for each environment. And maybe a bigger problem is that they're very inefficient in version 1 of the CLR. So instead, we play various tricks to share classes. For example, we have multiple apply methods within a single class and try and share environments where the types match up. Obviously, better would be to have support for closures in the runtime. No, probably not. They're going to make delegates more efficient, so that would be an alternative, yeah. But yeah.
Are your functions callable from outside of?
No, they're not. So we say the only stuff that you can export is pure CLS types, and functions don't fall into that category. Although we have support for delegates from within SML.NET. So you could create a delegate and wrap it around a function. Yeah.
But in the case where your functions are static, they don't have any closed free variables.
That's right, yeah. But we'll see in a minute that just having generics in the runtime, which is coming, is a big help for this. So I don't think we're too bothered about not having closures, actually. So the final feature is parametric polymorphism. So again, we could use the inheritance idiom. So this is what a C# programmer would do. You pick a uniform representation for values, and if you look at something like the collections class library in .NET, this is what they do. You use system.object for everything. The downside is that when you've got values with primitive type, those must be boxed on the heap, which is inefficient. And you need to cast every time you pull something out. I mean, this is the typical way that polymorphism is implemented in ML compilers, by the way. I mean, you use a uniform representation for values. But I guess they really try and optimize that as far as they can go, and we don't have that available in the CLR. So the alternative is to monomorphize, to specialize functions so that for every type that they're used at, you get a new piece of code. And of course, in theory, that means you get an exponential code explosion. But we don't see this. There's three reasons, probably. Firstly, we don't actually generate code for every single type instantiation. We only generate it where, with respect to the representation in the CLR. So sometimes we'll share types. So an integer is represented the same way as an enumeration value. So we'll only get one version of length in this case. And all the sharing that was going on in data types and functions helps us here. So the fact that we represent all data types by this universal type U means that we get less variance to specialize with respect to. The other thing is that specialization itself leads to further optimizations like inlining and so on. And just anecdotally, polymorphic functions tend to be small. If you're writing something that's very general, then it's unlikely to be very large. Now, the reason I'm here this month is I'm sort of finishing off design and implementation of generics for the CLR, parametric polymorphism. So version 2 of the CLR and version 2 of C# will support this directly. And this makes it much easier to compile SML and other functional languages. Not just the polymorphism feature of SML, but the fact that we had to generate all these classes for different types goes away. So, for example, we could have a tuple3 class that represents all 3 component tuples, and then just instantiate it with the appropriate types. And similarly, for function types, we could have an abstract class, fun, with argument and result type, and then just instantiate that. And then particular closures will extend that abstract class at their particular type, int in this case. So a good thing about this is that we don't have this name mangling problem, having to generate names for all these types. So we can almost support separate compilation, not quite. The two things that stop us quite getting to true separate compilation are, well, functors. I don't think there's any way we're going to get support for that in the runtime in the near future. And at the moment, there's no support in the CLR for abstract types. That's hiding of a type by a signature.
So this makes representation easier when you compile, but does it actually lead to efficiencies in after Pivot?
It should do, because the way that the generics is implemented is they specialize. So there's no the code you get out is almost as efficient as if you hand specialized the code, which is what we did. We did the monomorphization in SML.NET. We're just shifting it down to the JIT and loader. So it won't get better than what we've got, I don't think, but it shouldn't get any worse. So I'm going to talk a little bit about Visual Studio integration, which is something we've been doing more recently. So this is, most research compilers are just command line compilers, and often you sort of wish for all the nice features that you get in IDEs like Visual Studio. So, some of this you can do in Emacs, I guess, but not all of it. So the obvious thing being sort of syntax coloring and matching, completion of calls to library functions, debugger support, of course, and we've put in sort of continuous parsing and type inference. So as soon as you make a type error, then it flags it. So the way we implemented this was we sort of bootstrapped, well, part of the compiler at least, that to provide a .NET component, a .NET assembly that does parsing and type checking and so on. All the stuff you require of the sort of front end in VS. And then we used our interop feature to expose this as a COM component. So Visual Studio is not written in managed code yet. And to extend it with plugins and so on, you need to write a COM component, but you can actually wrap up .NET assemblies as COM components. You don't really need to know about COM, which is quite nice. And then wrote some new ML code to handle all the extra features we wanted. And I think this is the first time anybody's done this for Visual Studio, written something in managed code in this way to plug in. Right, so I'm going to demo that now. So this lives on another machine, unfortunately, because I've completely... this machine has got the generics build on it, so it doesn't work for Visual Studio right now. I think I'm going to have to skip that.
We could switch to the built-in PC.
Yeah, try that. Better. Right. Okay, so here we have some ML code with syntax coloring, with B. This is actually the game of life. And you see, it's actually a multi-language project. There's the actual sort of computation side of it is done in ML, and then it's hooked up with some C#. You can see here in the project window that does the rendering. So this is the server.sml file, and I'll just run it just so you can see. Right now it does a rebuild every time you run. Okay. Okay, and I can set breakpoints, for example, here. And run it again.
Can you set a breakpoint in C# and then step into the ML code?
Yeah. Yeah, that's the nice thing about the whole thing integrated. You can step across.
use ML variables and
Sorry, can you?
variables and their values and stuff?
You can only pass stuff across the boundary that is in the CLS, so you can. Is that what you mean? Can I look at them? Yeah, sort of. So. Okay, so it's hit that breakpoint, and I can single step. It's a bit because it's an optimizing compiler. You know, it's slightly strange. Some of the behaviour. Well, I don't know where we're going now, right? But so some of this stuff, you know, we're going to have to undo some of our optimizations to make it more debug friendly. Somewhere there is. Anyone know this?
Debug Windows.
From the debug, right? Visual Studio only me.
First thing.
Windows, right? So you can look at locals. So this is not. Some of this is okay. I mean, like there's size there, okay. But other stuff. So survivors, which I think is a list. Right. You know, they've got. If you know what you're doing, you can look inside. But because we're trying to share so many classes, we haven't preserved some of the names. So that's kind of.
When generics comes out, will there be like a convenient way to browse the data types and so on?
Yeah, I mean, generics will be supported by VS. So, I mean, a data type could almost map down to some classes, and it would.
But I mean, in a way that makes sense to somebody who's using it.
I think so. Yeah.
No, well, actually.
Okay. So that's.
Can I ask a question?
Yeah.
Did you have to write special code for that variable value, or did you just get that for free because your types were CLR types?
That was for free. So even if we'd not done any Visual Studio integration, that much would have happened. Yeah.
Okay, but the breakpoints you had to clearly have some special code to integrate with.
Breakpoints, it's enough just to put line number information in the IL file, and then Visual Studio will take care of the rest.
Okay.
So do you generate an IL file and then use ILASM?
Yeah, that's what we do right now. Yeah, if we didn't do that, we'd have to write the PDB files directly, what ILASM does for us. So what you've seen so far isn't really Visual Studio integration, I guess, except for the syntax coloring. But if you look here, there's this is a call to a method in the .NET library, and we can get a list of methods in system.console. So you get this kind of feature from C#, but now we've got it expressed in SML. Oh, it's gone. Last long. But you saw there was WriteLine is a heavily overloaded function, so it's got all these different signatures, but they're expressed using ML type.
Cool.
So you see object option, type of object, object option, so on. And we get completion as well. So if I was to type, for example, system.console. That doesn't sound very. Oh, awesome. Oh, right, there we are. It's completing. And now I open a bracket. It tells me I've got all these 19 different. It's telling me I'm now expected to type in a string option. That's in bold. So I'll type in. Oops, good. And now.
Now does the SML, like I've looked at your documentation and I know that sometimes you automatically coerce a string to a string option.
Yeah.
Does that happen only to exported type? I mean, like,
yes.
Imported types, or does that happen sort of generally?
That only that only happens for interop types. Yeah. So it'll also pick up syntax errors on the fly. If I do val val equals 1, say, then somewhere. There you are. Red squiggly. And it would have done the same for a type error. The error itself, I think, appears in the task window, wherever that is.
Can you highlight something and figure out what its best guess type is?
Not right now, no. But that's an obvious thing to put in. I mean, this IntelliSense stuff should also work for ML libraries as well as .NET libraries. Right now there's some sort of bug that's stopping that working. So I could, for example, type list dot and then get completion and types and so on for that. So there's a whole, I mean, it's, you think it's kind of cosmetic stuff, but just having it makes us realize there's lots of possibilities here for making programming these languages much easier. Sort of wizards that take data types and generate functions for you, for example, that kind of thing. Just the fact that maybe the IDE understands the notion of scope would be very, very helpful. So I guess that's it, really. Are there any other questions?
Yeah, I'm curious about how you do the dynamic error detection. I mean, you have a traditional parser, or how are you doing this online? It's always been a mystery to me how you type and get feedback.
We're just doing traditional parsing. We had to fix up it's using ML-YAC. We had to fix it up so that it was sort of non-stateful. But apart from that, we're just... So
if you're typing online, what's the context you're parsing when somebody's typing and hitting return?
The whole file.
Oh, okay, so you're just redoing that. Okay.
Yeah, I mean, a future thing would be to do things incrementally, which...
I see. So you're not doing anything fancy.
No, I mean, C# does that, but
right.
I mean, it's a lot harder in the context of ML with type inference.
Yeah.
Do that kind of thing.
So you mentioned that you do show type errors too.
Yes. I don't know whether that feature's quite working.
Because that's one of the things that in ML you have a very non-local type inference. So how does that look? I'm just curious if that's working.
What's being suggested is I do this. For the purposes of the demo. Here's a type error. So it should just... What should happen is you pick up the error and flag it underneath. But I think that feature's not working right now.
Okay.
But yeah, I mean, you're right. Even without Visual Studio, the interaction of type inference and our interop is a problem because we're doing all sorts of things like implicit coercions and widenings, as well as doing ML-style type inference, and the two don't quite fit. What you get is mostly what you want, actually. You don't often get surprised, but it's hard.
So in this example, it looks like you have a C# executable that's calling into SML?
Yeah, that's right.
What's at that boundary?
So the boundary, I'm not sure this is a very pretty example, but have a look at the C#. Ooh, that always happens. Right, here's the C#. So there's some kind of factory class, I think he's called it. It's not my code. So I think, yeah, right, there's a class which I think ML implements. So if you look at classes.sml, got a lot of red squiggly there, I don't know why. Okay, so there's some extensions here that we didn't see earlier. We've got a new class defined inside of ML. In fact, a couple of them. And I think C# just calls into those classes, creates instances of those classes, and calls methods on them. But you can get away without classes even, because you can export an ML structure, and any top-level functions in the ML structure get exposed as just static methods. So you don't even need this. You can actually take just a pure ML program and sometimes just export it to C#. Yeah.
How does this relate to other similar work at Cambridge? I mean, as far as I know, there's the ILX stuff that implements a lot of the same thing at a more assembly level, and there's a CAML porting effort, and so on. Are you guys using all the same technology? A lot of what you were talking about in terms of how you've encoded some types and so on looked really familiar from some of the other efforts.
So, yeah, so the other projects in Cambridge, so Don Syme has worked on this, is ILX, he calls it, which is an extension to IL to support, well, those three features, in fact, data types, polymorphism, and functions. And then ILX compiles down to IL, or possibly to IL with generics for V2. We haven't used that, mostly because we already had a compiler that was for Java, and we've been porting that to SML.NET. I think if we'd started from scratch, we might have considered using Don's library. And then the other thing that Don's done is this compiler for Camel, which he's recently released. He calls it F#, try and distinguish it a bit from Camel. And it's taking a sort of different approach. So he's trying to do quite a simple compiler. So it doesn't do like whole program analysis or optimization. But what it does do is it lets you compile down some Camel code and then access it from C#, including data types and functions and everything. Whereas we've been sort of assuming you've got lots of .NET stuff and you want to write ML code to access it rather than the other way around. So yeah, but you know, we could borrow features from each other, sure. Yeah.
Two questions actually. The first one is, this grew out of the MLJ projects, right? So what kinds of what kinds of differences did you find going to .NET?
So there's a lot more.
Easier? Was it harder? Was it?
It was harder in some ways because we had to support a lot more interop. Because there's a lot more features in .NET in this CLS that don't exist in Java. For example, delegates, value types, custom attributes. I could go on. Perhaps the hardest is call by reference, for which we've sort of extended the ML type system. In terms of compilation, the fact that we've got tail calls helps. And there's other things in there we could use but don't right now. So the fact that you can do call by reference and take the address of values and you can take the address of the interior of objects on the heap, for example. There's optimizations to do with turning non-tail recursive functions into tail recursive ones where you pass around pointers. So you can do a lot of list functions like map and append and so on. It's called tail cons optimization sometimes. And I think we could really benefit from the support for call by reference.
The second question had to do, so SMLNJ runs entirely on a heap, and I was kind of curious, like, what kinds of, or almost entirely on the heap except for the loader. So what kinds of restrictions does running in the IL give you? For example, like, do you run entirely on the heap, or do you also use the stack, or how does it?
So the question was about other implementations of SML using the heap entirely rather than just the stack as well. And yeah, that is a problem because if you've got a deeply recursive function that's non-tail recursive, then we just use the stack. We don't allocate frames on the heap. So you often have to, well, not that often actually. You sometimes have to set the stack size in the executable to be sufficiently large. But we've not actually found it to be a problem.
Right.
I mean, where it would really be a problem is if you want to implement something like call CC, where you really do want to capture the stack on the heap, and that's just not possible with CLR. Yeah.
Was there any place in your implementation where you were really missing inner classes?
No, because inner classes are compiled down to non-inner class based JVM. The JVM doesn't support inner classes directly. So in fact, we actually allow you to do inner classes in the interop feature. You can have a class type declaration, inside of a function, say, or you even have an anonymous inner class is supported in something like that. Yeah.
Oh really?
Yeah. So it's a matter of compiling to that.
Have you talked at all to the people working on X# that they specifically put together or are putting together a framework for writing managed code which interacts with Visual Studio to do some of what you've done here?
Oh, I didn't realize the Visual Studio connection. Yeah, I mean, I've talked to Eric Meyer a bit.
Helmut was working. Helmut, no.
Wolfram.
No. But they were working on a set of classes to specifically facilitate this. They're also working on a whole compiler structure for more procedural class type compilers.
Right.
But one of the things they were doing was trying to make this easier and had a whole set of things to do exactly what you're doing here, all in managed. and
Right.
all the interop was taken care of by their layer.
Well, what we are using is a library called Babel, which was developed by Dan Lyon, who was an intern here for 3 months. So that is a sort of interface between the big hairy Visual Studio API and giving it a friendly interface, and it also gives support for grammars and syntax highlighting. So we've used some of that, but not all of it. Yeah. So I don't know whether Eric's using the same stuff. But yeah, we should talk to them, I guess, if someone's trying to come up with a common interface.
I have 2 projects here. One is all C# and the other is all ML.
That's because Visual Studio doesn't let you have multi-language projects. It only lets you have multi-language solutions. A solution contains many projects. I think that means you can't have a DLL containing things from different languages. But
Do you know what that restriction comes from? Is it
no, I have no idea.
And actually, you can.
Oh, you can.
You make multiple projects which generate libs, and then you have another project which builds a DLL from the libs.
Oh, right. Okay. Thanks.
Can you generate libs from C#?
It's sort of.
Okay. Thank you very much.